Okay, here's a quick tutorial for section 4.7 combinations. So if you remember from the last lesson, section 4.6, we looked at what permutations were, and we learned that permutations are ordered arrangements of objects. And I showed you the formulas for calculating how many ordered arrangements of a certain number of objects you can have. If we wanted to figure out how many ordered arrangements or permutations of n objects there were, all we had to do was n factorial. And I explained to you what factorials were in the previous lesson as well and how to calculate factorials. So make sure before you're watching this lesson, you've watched the 4.6 lesson so that you're clear on all of this. Also, we looked at the number of ordered arrangements of n objects in which some of the objects were alike, and I showed you this formula: n factorial equals a factorial over b factorial times c factorial, and so on. And I explained to you why we're dividing by a and b and c factorial, and so on, depending on how many alike objects there are. I then showed you the formula for if we wanted to figure out the number of ordered arrangements of n objects if we take them r at a time. So if we only wanted to take part of the group, we had to divide the n factorial by n minus r factorial. And in the previous lesson, I showed you how to calculate this by hand, the shortcut on the calculator, and I also explained the rationale behind, first of all, behind the n factorial that's on top, and also I explained the rationale behind the n minus r factorial on the bottom. So make sure you've watched that previous lesson so you're clear on all of that. Okay, so remember, this summary here is for permutations. So that's ordered arrangements of objects. Today the lesson is going to be on combinations, which are slightly different. So I'm going to take you through this first example to hopefully clarify the difference between combinations and permutations. So this is a very common problem to use when talking about combinations, but let's read it and try and think of some possible ways we could solve this problem before I teach you the formula for combinations. So in my data management class, there are 26 students. Okay, and for the purpose of this example, pretend you are one of the 26 students. If every student shook every other student's hand once, how many different handshakes would take place? So I have 26 students in the class. You are one of the 26 students. If every student in the class shakes every other student's hand once, how many handshakes have taken place? Well, if we think about that logically, okay, you are one of the students. You are one of the 26. How many handshakes are you going to have to give? You're going to have to shake the hand of all of the 25 other students in the class. You personally are going to have 25 handshakes. Now, every other student in the class is also going to have to shake every other student's hand, so every other student is also going to have 25 handshakes. So all 26 students are going to give 25 handshakes. So to calculate the total number, you might say it makes sense, just do 26 times 25, because 26 students are each going to give 25 handshakes. So we do 26 times 25, that'll tell you the total number of handshakes. Now that might make sense, but you're forgetting the fact that, let's say your best friend's name is Dave. When you shake Dave's hand, you've counted that as one handshake, but Dave has also counted that as one of his 25 handshakes. So you have counted that handshake twice, even though it is in fact the same handshake. And that's going to be true for every pair of handshakes. Each person in the pair will have counted that handshake once. So we've counted each handshake twice, even though it's only one distinct handshake that is happening. So the next rationale I'm putting up here may help clarify that. So however, this would count the handshake between each pair twice. And in this instance, the order does not matter. It doesn't matter when you're shaking hands. It doesn't matter if you're shaking Dave's hand or if Dave is shaking your hand. It's one handshake that is taking place. So the order does not matter. So this is different than permutations. Therefore, we have to divide our answer by 2 because we counted every handshake twice when it should have only been counted once. Another way to think of it, so we're forming groups of 2 in the class. So there's 26 people. We want to figure out how many different handshakes can we make. So how many different groups of 2 can we make? Now when we make a group of 2, you and Dave are a group. That's one handshake. But how many different ways could we arrange that group? We could have arranged it you and Dave or Dave and you. So how many different arrangements are there for 2 objects? There's 2 factorial. So we have to divide by 2 factorial because for each group of 2, we've counted it twice when we should have only counted it once because the order does not matter. Okay. I'm gonna try and explain it like that a couple more times as we do the examples, just so you kind of understand why we're gonna be dividing by, r factorial, and I'll explain that more when I give you the formula. But basically, here's the difference between permutations and combinations that should be pretty helpful. So permutations are ordered sets, where let's say we have the letters A, B, and C. A, B, C is different than BCA, which is different than CAB because they're in different orders. Okay, so if we're talking permutations, all three of these sets would be considered different things because they're in different orders. However, for combinations, okay, order is not important. So when you have a counting problem, sometimes the order of the objects is not important. So if the counting problem has to do with combination, something where the order is not important, the set ABC would be considered the same thing as set BCA, and it would be considered the same thing as CAB because it has all of the same elements in each set. The fact that they're in different orders doesn't matter if we're talking about combinations. So permutations, order matters. Combinations, order does not matter. All right. Here's the formula for calculating permutations and combinations, and I explained this formula in the last lesson if you want to go back and watch it. Here's the formula for permutations. Here's the formula for combinations. And you'll notice they're very similar with one key distinct difference. We're going to be dividing by r factorial in the combination formula. Because it may be easier for me to explain this as I'm going through an example, but I'll give it a quick shot here. Let's say we have 8 objects. We want to figure out how many different groups of 3 can we make. Well, if we use the classic permutation formula, we would have 8 factorial over 8 minus 3 factorial, which is 5 factorial, and that would simplify to 8 times 7 times 6. 8 times 7 times 6. So that would tell you how many ordered groups of 3 we can make. That considers the order of the objects. But if we did that, here's our letters A, B, and C. It would have counted A, B, C as being different than BCA, which is different than CAB, and so on. So for each set, if one set is A, B, C, we would have counted that too many times because we would have counted these things as being different, but with combinations, they're not different. So how many times too many did I count each set? Well, how many different ways can I arrange 3 objects? And we learned earlier through how many ways we can arrange 3 objects. Hold on, let me just write it over here because we're now going to do the formula for combinations. How many different ways can we arrange 3 objects? Well, just do 3 factorial. So we're going to be dividing by 3 factorial. Because in 3 factorial is 3 times 2 times 1, which is 6. So for each arrangement or each group of 3, we would have counted it 6 too many times. Because for each group of 3, we could rearrange the letters in 6 different ways. So we would have counted each group 6 times too many, because these things would have been the same. ABC is the same as BCA, which is the same as CAB, which is the same as ACB, and so on. There are 6 ways I could rearrange those letters. That's why I have to divide by 6, or 3 factorial is how we calculate it. There are 6 different ways to arrange 3 objects. Okay, let's put this formula into use. So let's revisit the handshake example using the combination formula. So the combination formula, you'll see it either written as a C and then the N and the R in brackets, or you'll see it written like this, in brackets with an N and an R below it, or you may see it as NCR, and this is the way you'll see it on your calculator. This is probably the most common way to write it within problems as you're doing your solutions. But for the handshake problem, N is the number of elements in the group, or the number of elements total, and R is the number of objects we want to consider. So for example, in the handshake problem, there are 26 students in the class. I want to figure out how many combinations, if we take the 26 elements 2 at a time. So how many groups of 2 can we make from 26? So the way I would say this is 26 choose 2. And use the formula n factorial over n minus r factorial times r factorial. So let's actually go ahead and calculate how many different handshakes are possible. So I would have to do 26 factorial. Keep in mind, here's your n, here's your r. So I have to do 26 factorial over n minus r factorial. So 26 minus 2, which is 24, so 24 factorial, times r factorial in the denominator as well, so times 2 factorial. So I need to divide by 2 factorial because that's the number of ways I could arrange the people in each handshake. So I've counted them each handshake twice too many times, so I got to divide by 2 factorial. So if I calculate this, we could expand out the top and the bottom and cancel out pairs of factors. I'm going to simplify 26 factorial to 26 times 25. Then it would keep going times 24 times 23 all the way down to 1, but I could end the expansion by putting a factorial symbol. So this means 26 times 25 times 24 factorial, and 24 factorial lets you know that it keeps going all the way down to 1. And on the bottom, I have 24 factorial times 2 factorial. Now these 24 factorials will cancel out. I could also simplify 2 factorial is just equal to 2, because 2 factorial is 2 times 1. So 2 factorial, 26 divided by 2 factorial would be 13. So really all I have to do is 13 times 25. And I'll also show you a shortcut on your calculator for doing this as well. So you can just do 13 times 25 and you can get your answer. Or you could do you could type this, the 26 choose 2 on your calculator. So you have 26 objects. How many different groups of 2 can you make? Well, you type 26, go math over to probability. Number 3 is the combination. So 26 choose 2. This will tell you how many groups of 2 you can make from 26 if the order does not matter. And you see you get the same answer either way. We get 325 different groups of 2 we can make from 26 objects. So for the problem with making handshakes in the class, there would be 325 different handshakes taking place in the class if all 26 students shook every other student's hand once. Okay, let's do another example. Let's say you won 4 free tickets for the 2014 Stanley Cup Final. Hopefully it'll be Pittsburgh versus San Jose. So currently, as I'm making this video, we're in the first round of the playoffs in 2014. Pittsburgh's tied 1-1 with Columbus, and San Jose is up 2-0 over LA. Hopefully they both make it to the final. So you won 4 free tickets to the Stanley Cup Final. So obviously you're going to use one of the tickets, and you want to figure out how can you pick, let's say you have 10 best friends. How many different ways, or how many different groups of 3 could you make from your 10 best friends? So we have 10 best friends, there's our N, and we want to figure out how many different groups of 3, there's our R, could we make? So, I'm going to explain this to you a couple different ways. So first of all, we have 3 spots that we can pick friends for. Okay, so we could pick. We need to pick 3 friends. 1, 2, 3. So I named my friends with letters A, B, C, D, E, F, G, H, I, J. I could pick any one of these 10 friends for the first spot. Any one of them. Let's say I picked friend A. Okay, but basically I had 10 options for my first spot. I had 10 options. For my second friend, I have 9 friends left to choose from, and for my last friend, I have 8 friends left to choose from. So I could have chosen B for the second one, and then I had 8 left for the third choice, C. So to figure out the number of different ordered arrangements of friends I can make, I would just do 10 times 9 times 8. Okay, which would equal, I could have used the permutation formula, 10 factorial over 10 minus 3 factorial, which is 7 factorial, and that would simplify to 10 times 9 times 8. Same thing. Okay, I could have done that, but keep in mind for this question, you need to ask yourself, does the order I pick my friends really matter? Does it really matter if I pick friend A, then B, then C to go, or if I pick friend B, then A, then C to go? No, the order doesn't really matter. All 3 of them are going to end up coming to the game. It doesn't matter what order I pick those 3 friends in. So how many different ways could I arrange these 3 people, and they're all still going to be coming to the game. It doesn't matter what order I pick them in. So I need to divide by how many different ways could I arrange these 3 objects, because I've counted it that too many times. So how many ways can you arrange 3 objects? Just do 3 factorial. And I'll tell you how many ways you can arrange 3 objects. So for each group of 3 that I could make, I will have counted it. Well, 3 factorial is equal to 6. So I would have counted it 6 too many times. So I'm going to end up dividing my answer by 6. Now, instead of doing it this way, I'm just explaining to you where the formula is going to come from. So now I'm going to use the combination formula, and show you how we're going to get to that same thing that I just had there, 10 times 9 times 8 over 3 factorial. So the combination formula tells you to do, I have 10 objects, and I want to figure out how many groups of 3 can I make. So 10 choose 3. So I'm going to write it this way this time. This means 10 choose 3. N is on the top, R is on the bottom. The combination formula is n factorial, so 10 factorial, over n minus r factorial, so 10 minus 3 factorial, times r factorial, so times 3 factorial in the denominator. Let's simplify that. So that's 10 factorial over 7 factorial, 3 factorial. Now, if I expand out 10 factorial, that's 10 times 9 times 8 times 7, so on. I can end my expansion by putting a factorial symbol over 7 factorial, 3 factorial. 7 factorials cancel, and look, I'm left with 10 times 9 times 8 times 3 factorial. And you'll notice that's the same answer I got to using that other method, the multiplication rule for counting that I was talking about before. So you can do it either way, think of it either way, but feel free to do it this way. And then if we were to evaluate that, 720 divided by 6, so we can do it on our calculator, 10 times 9, 10 times 9 times 8, and divide by 3 factorial, and 3 factorial is 6. And I get 120. You can also type it on your calculator, the shortcut. So I have 10 objects, 10, then go math, probability, number 3. That means 10, choose 3. This means how many groups of 3 can I choose from 10 objects, and once again it's 120. So my answer, I can make 120 different groups of 3 from 10. So there are 120 different groups of 3 friends I could pick from my 10 friends to go to the game with me. Okay, so that's the last time I'm kind of going to show you different ways to solve the problem. From now on, we'll just use our formula here, or maybe even I'll just use the shortcut on the calculator from now on. So, from a class of 30 students, determine how many ways a 5-person committee can be selected to organize a class party. So, first thing you should ask yourself, when I'm making a committee of students, does the order I pick the students in really matter? In this case, the answer is no, the order doesn't matter, so we're going to be using combination. Okay? So for combinations, we'll use the combinations formula. NCR equals n factorial over n minus r factorial times r factorial. There's the formula. So I'm probably just going to use the shortcut on my calculator for this one. So from a class of 30 students, so there are the total number of elements. Okay, there are 30 students. How many ways can a 5-person committee, or how many ways can I make a group of 5 from 30? So I need to do 30 choose 5. So you'll see it written like this. 30 choose 5. Maybe you'll see it written like this. 30 choose 5. You might see it written either way. That would equal 30 factorial over 25 factorial times 5 factorial. And we could write it out like that, but I'm just going to do the shortcut on the calculator now that we know how to use the formula. So all I have to do is 30 math probability choose 5. And there are a lot of different 5-person committees I can make from 30 students. 142,506. 142,506 different 5-person committees I could make from the 30 students. Now, the question gets altered a little bit. How many different committees could I make if Marnie has to be on the committee? So if we think about it, if Marnie has to be on the committee, she's going to be in all the different variations of committees I can make. I now only have 4 spots left to fill on the committee. So my R value is now only 4. I'm only considering about how many different ways can I make a group of 4, because Marnie's for sure going to be on the 5-person committee. And so the number of people I have to choose from is now only 29, because Marnie's been taken out of that. She's already for sure on the committee. So I now have 29 people to choose 4 from. How many different ways can I choose 4 people to fill the rest of the spots on that 5-person committee from the group of 29? So all I have to do is 29, choose 4. Or once again, you might see it written like this. And we can type that on our calculator. 29, choose 4. How many groups of 4 can we make? 23,751. 23,751. Okay, let's do another example. I like this problem. How many 5-card hands can be dealt out of a deck of 52 cards? First thing you have to ask yourself, does the order of the cards in your hand matter? And the answer would be no. If you have 5 cards in your hand, it doesn't matter what order those cards are in. You have all 5 of them. You can arrange them however you want, and you still have the same 5 cards in your hand. So order doesn't matter. So once again, we're going to be doing combinations. There are 52 unique cards in a deck. How many different groups of 5 can I make if the order does not matter? We'll have to use the combination formula. So I need to do 52, choose 5. So on your calculators, do 52, choose 5, and there are a lot of hands. 2,598,000, 2,598,960 different 5-card hands you can make from a deck of cards. Okay, this is where I'm going to do 2 more examples, and this is where the problems are going to get maybe a little bit more complicated. You're going to have to remember a couple things. You're going to have to remember the multiplication rule for counting. So what that says, it says to find the number of outcomes for a series of events, find the product of the possible outcomes at each step in the sequence. So that just means how many outcomes are possible for each step, multiply them together, and that tells you how many possible outcomes you have. So now let's look at this problem. A coach of a co-ed basketball team must select 5 players to start the game from a team that consists of 6 females. So we have 6 females, and I'll use blue for males, and we have 5 males. So we have 6 females and 5 males. And the coach has to pick five players to start the game from these 6 females and 5 males. How many ways can this be achieved if Tanya, I'm guessing Tanya's the coach, sorry, she must choose 3 females. She must choose 3 females and 2 males to start the game. So, we have to choose 5 people in total, 2 of which are males, 3 of which are females. So, if I want to figure out how many ways that can be done, okay, let's figure out how many, remember the multiplication rule for counting. And whenever you say the word and when you're thinking to yourself, this word and is important. Whenever you think and, think multiply. If I need to make a starting lineup that has 3 females and 2 males, figure out how many ways could I pick 3 females from the 6, and multiply that by how many ways could I pick 2 males from the 5. So let's write that out. To figure out the number of starting lineups, all I have to do is I need to do 6 choose 3. That'll tell me how many ways I could choose 3 girls from the 6 that are on the team. Times, now let's look at the males. I need to choose 2 of the 5 males. And let's see what we get here. So 6 choose 3. 6 choose 3. There are 20 different groups of 3 of the girls I could make from the 6 that are on the team. Then how many ways could I choose 2 of the 5 boys? Just do 5, choose 2. And there are 10 different ways I can make groups of 2 from the 5 boys on the team. So now to figure out the total number of starting lineups of 5 players I can make that consists of 3 females and 2 males, multiply those 2 numbers together, and I get 20 times 10, that'll give me 200 different starting lineups I could make that consist of 3 females and 2 males. So remember, this multiplication rule for counting is crucial. If we want to figure out how many groups I can make of 3 females and 2 males, when you see the word and, think multiply. So how many ways can I pick 3 times how many ways can I pick 2 males? And that'll give you the total number of possible lineups that consist of those 2 things. So I'll give another page for this solution here. This might have been better to lay it out this way. How many ways can I choose 3 females from the 6? Well, we did 6 choose 3. How many ways can I choose 2 males from the 5? I did 5 choose 2. And I got 20 times 10. Gave me 200 different lineups. Okay, last example. In how many ways can 6 people be selected from a group that consists of 4 adults and 8 children? So I have 4 adults and 8 children, if the group must contain at least 2 adults. Okay, this word at least is going to change up some stuff for this question. So how many ways can 6 people be selected from a group that consists of 4 adults and 8 children? So there's 12 people in total. How many groups of 6 can I make if the group must contain at least 2 adults? So there's different possibilities here. The group could have 2 adults, or 3 adults, or 4 adults. So we could have 2 or 3 or 4 adults in the group. I can't have 5 adults in the group because there's only 4 adults to choose from. When you see this word or, you need to be thinking add. Okay, so you'll have to remember the additive principle for the union of sets. When you think or, think plus. So it's how many ways could I have a group with 2 adults? How many ways with 3? How many ways with 4? Add them together. So keep in mind, if we have 2 adults in the group, if I have 2 adults in the group has to have 6 people. That must mean there must be 2 adults and 4 children. Or if there are 3 adults in the group, that must mean there are 3 children because I need to have 6 people in the group in total. Or if there are 4 adults in the group, that means the other 2 people must be children in the group. So a lot's happening here. I have 2 adults and 4 children. So remember, and, we need to multiply. Or means plus, 3 adults and 3 children, multiply. Or 4 adults and 2 children. So I need to figure out how many different groups can I make of 2 adults and 4 children by multiplying the number of ways I could choose 2 adults from the 4 times the number of ways I could choose 4 children from the 8. Do the same thing for how many ways could I have a group of 6 if 3 of them are adults and 3 of them are children. And same thing for the number of ways I can make a group of 4 of them are adults and 2 of them are children. And then add each of those results together because it's possible for any of those 3 conditions will satisfy there being at least 2 adults in the group. Okay, so let's go ahead and actually do this solution. So I want to, maybe I'll just copy this, this part over to the other slide so you can see what I'm doing there. Okay, so this is the first way we could satisfy there being at least 2 adults in a group of 6. There would be 2 adults and 4 children. That's one way it could be satisfied. So if I'm going to have 2 adults and 4 children, I'll use red for adults. I need to have 2 adults. So how many different ways could I choose 2 adults from 4? Well, I have to do 4 choose 2. But also, remember, the group also needs 4 children. I need 2 adults and 4 children. So I need to multiply that by how many ways could I choose 4 children from, I think there were 8 children to choose from. So times 8 choose 4. Now, that's one way I could satisfy the condition. Or, so plus, I could satisfy the condition by having 3 adults. So how many ways could I choose 3 adults from the 4 and multiply that by, if there are 3 adults in the group of 6, that must mean there are now 3 children. So how many ways could I choose 3 children from the 8? And the last way I could satisfy the condition is I could have 4 adults in the group. So how many ways could I choose 4 adults from a group of 4 and multiply that by, if there are 4 adults, there must only be 2 children from the group of 8. So let's go ahead and evaluate this, and don't forget BEDMAS, do all your multiplication first, but let's evaluate our combinations to start off with. So let's figure out, okay, well, what is 4 choose 2? 4 choose 2 will give you 6. And then we're also going to need 8 choose 4 for our first part of our equation there. So I need to do 6 times 70. I'm just going to do the rest of this in black. 6 times 70 plus 4 choose 3. Okay, that would just give me 4. I'll just go ahead and do that without typing it in. And 8 choose 3. 8 choose 3 will give me 56. Plus 4 choose 4 is 1. Well, how many different groups of 4 could we make from 4? Well, there's only one way we could do that. And 8 choose 2. 28. So let's go ahead and do all these calculations. 6 times 70, that'll give me 420. plus 4 times 56. Well, 4 times 50 is 200. 4 times 26 is 24, so I'll do 24. Plus 28. I should have equal signs in front of all of this here. And lastly, we have 420. Oops. Plus 224 plus 28, 672 different groups of 6 that contain at least 2 adults. Okay, so that's one possible way you could have got to the solution. I'm going to explain another way. I'm probably not going to write it all out though, because I don't want it to take too long. Another way we could have done this in this situation, we could also figure out the number of groups that have at least 2 adults. By subtracting the number of ways the condition cannot be satisfied. So if we can figure out how many ways could we have 0 adults or 1 adult in the group of 6, and subtract that from the total number of combinations. So I'll write out the formula, but I won't actually do it all for you here. So what I could do, I could figure out, okay, how many different groups of 6 could I make from, there were 12 people in total, 4 children, or 4 adults, 8 children, so 12 people in total. I could calculate how many different groups of 6 could I make, and then subtract the number of ways that the condition could not be satisfied. So it could not be satisfied if I had 0 adults. So that means I'm going to choose 0 of the 4 adults and 6 of the 8 children. Or I could have 1 adult in the group. 4 choose 1, and that means I would then have 5 of the 8 children. So I could then calculate this, and that should get me to the same answer, 672. Okay, so that's it for this lesson. That's it for permutations and combinations. Remember, use the formula for permutations when the order of the objects matters, and use the formula for combinations when the order of the objects in the group does not matter. Make sure you go to jensenmath.ca, download the worksheet, and make sure you practice. Let me know if you have any questions.